All right, so in the previous video, we developed the theory for the form of the zero input response solution to a difference equation. What we're going to do now in this and the next few videos is actually work through some specific examples of solving for the zero input response for different difference equations. So here in this first difference equation example, we'll deal with a difference equation that actually has distinct roots, and we'll figure out what the zero input response is. All right, so our first difference equation example that we will solve for the zero input response is given by this difference equation right here. So we have a discrete time, linear time invariant system described by this difference equation right here, y of k plus 2 minus 0.8 y of k plus 1 minus 0.09 y of k equals 3 f of k plus 2. So again, the notation we use, f is usually an input. Some books like to use x of k, but our input here is f of k. And we are going to find the zero input response. That's kind of the section we're talking about right now. Remember, the zero input response is due solely to the initial conditions of the system. We're going to assume the input is 0. So the only way something can happen in the system is if there were some initial starting conditions. The starting conditions here are given by, at time minus 1, the output was equal to 0, and at time minus 2, the output was equal to 10/3. So those are the starting conditions of the system. If you remember, we had our operator notation video a video or two ago. Let's go ahead and rewrite the difference equation using that advanced operator notation. So remember what we do, we replace time shifts with e's raised to the appropriate power. So y of k plus 2 becomes an e squared y of k plus 1 becomes an e, etc. So we can rewrite that difference equation using our operator notation. Same thing on the right side of the equation. And then once we have it written in our operator notation, it's very easy to identify the characteristic polynomial of the system. This is q of e, so q of gamma, replace all the e's with gammas, and we now have the characteristic polynomial of the system. And that's that very important quantity because that defines the modes of the system based on the roots of this polynomial. So how do I get the roots of the polynomial? I set that characteristic polynomial equal to 0, and that gives me what we defined as the characteristic equation. So here is the characteristic equation of the system. And if I go ahead and factor that, define when this characteristic equation is equal to 0, in this case it's pretty easy. One of the factors is gamma minus 0.9. The other factor is gamma plus 0.1. I can now figure out the roots of this polynomial. The first root, when gamma is equal to a positive 0.9, I get a 0 there. So one of the roots must be 0.9, so I'm going to call that gamma sub 1. And then if I look at this term right here, if gamma is equal to a negative 0.1, I get a 0. So my other root must be negative 0.1, so I'm going to call that gamma sub 2. So now I have the two roots to my characteristic equation, and we now know what to do with those. Those I use to form the characteristic modes of the system. I take each one of those roots, raise it to the power k, and then I put a constant in front of it. So I have to do that for the first root, so there's my first mode, plus the second root raised to the k becomes my second mode. Remember in words we said the zero input response was always equal to. The zero input response is always a linear combination of the characteristic modes of the system. So that's exactly what I've done right here. I've taken a linear combination of the characteristic modes of the system. This case was pretty easy because they were distinct. We'll worry about the other cases in the subsequent videos for repeated roots and complex roots. The only thing left to do now is I need to solve for these unknown constants, those linear combining coefficients, the C1 and C2. I need to solve for those, and the way I solve for those is via the initial conditions. So let's figure that out. At time minus 1, I was told that the system output was 0. So 0 has to equal this equation with all the k's replaced with negative 1. So I do that. I replace all the k's with negative 1. Similarly, I was given an initial condition for time k equals negative 2. We were told that at time negative 2, the output was equal to 10/3. So 10/3 has to equal this equation with all the k's replaced with negative 2. So I do the exact same thing here, replace all the k's with the appropriate value. And now it's just time to do a little algebra to solve for these constants. I have two equations, two unknowns, just need to solve for C1 and C2. So let's simplify this equation right here. So 0.9 to the negative 1 is really 9/10 to the negative 1, which I invert, becomes 10/9. Same thing right here. 0.1 is 1/10. 1/10 to the -1 is 10 over 1 or 10. There's also a negative sign I have to worry about. So this simplifies to this equation. And then I can do similar work here to just simplify the algebra. Let's get rid of those exponents. 0.9 to the -2 becomes 100 over 81. 0.1 squared becomes 100. So I now have this equation. So this looks a little bit nicer in terms of just trying to solve for these constants. Anytime I have a system of linear equations, I like to write it in matrix form. So here are my two unknowns, C1 and C2. The coefficients, 10/9 and -10, go right here in this first row. And this is equal to 0. And then for the second equation, very similar thing. The coefficients, 100 over 81 and 100, go right here in this row. And this has to equal 10/3, obviously. And then if you have a calculator, you can plug in a system of equations, or if you have MATLAB, that's how I usually solve things like this. If we go ahead and do that, we figure out that C1 is equal to 27 over 100, and C2 is equal to 3 over 100. So now that we know those constants, we now know the zero input response. We just go back to our equation up here and replace those constants now that they've been solved for. And my final answer is this for the zero input response. So that's the end of this example. We solve for the zero input response of a difference equation for the case of the difference equation having distinct roots. In the subsequent video, we'll look at the case when there are repeated roots. Thanks for watching.